Hello, my name is Zhongyuan Zhao. In this talk, I'll present our paper on delay-oriented distributed scheduling using graph neural networks. This is a collaborative work with Gunjan Verma, Ansuran Swami, and Santiago Segura. Our work is about wireless multi-hop networks. The key feature of this type of network is that the nodes are autonomous and self-organizing. And it has wide applications in both mobile ad hoc networks as well as infrastructure-based networks such as 5G and the beyond.
First, I want to do some basics on the distributed scheduling. So we are considering a time-slotted network. All the devices are synchronized, and the system is divided into time slots. For each time slot, there is a scheduling phase followed by data transmission. The scheduling is based on the concept of conflict graph. The vertex in the conflict graph represents a link in the wireless network. An edge in the conflict graph represents that either there is an interference conflict, such as these two links that are close to each other, or there is an interface conflict, such as these two links. They share the same user. So for the orthogonal access, this means that a schedule is an independent set on the conflict graph. For example, if this vertex is scheduled, then its interfering neighbor should not be scheduled. So independent set basically says that it's a set of vertices that there's no edges between any of them. So in this way, we can formulate an optimal scheduling as a maximum weighted independent set problem. Basically, we want to find an independent set that has the maximum weights, maximum total weights. So the node weights is the per link utility function. And usually, we need to solve independent Morse problem across different time slots. And notice that this Morse problem is NP hard, so that instead of using optimal scheduler, we usually choose heuristic scheduler to find approximate solutions in practice. And notice that this independent set problem across time slots is usually formulated for throughput maximization. Now let's compare the optimal and greedy schedulers on a simple case. So here's a network with 6 links, and the conflict graph is a star-shaped graph. So the per link utility is the queue length, and the arrival rate is 1, the link capacity is 2. Initially, all the queues are empty. On the right-hand side, we show the steady-state transitions under the optimal scheduler and the greedy scheduler. So on this graph, there is 2 maximal independent sets. One is the peripheral, and the other one is the central node. As you can see that the average queue length under the optimal scheduler is longer than the average queue length under the greedy scheduler. So that means that the latency performance under optimal scheduler is worse than the greedy scheduler. So this is a well-known problem for queue length based per link utility that is a poor delay performance. So over the years, there are many approaches being proposed to address the poor delay performance of maximum weight schedulers. Among these approaches, what we're looking at are several properties. First, if they can be implemented in a distributed fashion. Right? The second is that if they follow hard constraint or soft constraints on the orthogonality. So these 2 properties determines how well they can be scaled to large networks. As you can see that the previous generation, the most successful approach is the delay-aware per link utility functions, which has very good properties in terms of scalability. And our approach follows a recent trend that uses machine learning to exploit the topology of the network, while our approach keeps all the good properties of the previous generation of solutions, and we complement them by exploiting the topology of the network. Next, I will introduce the formulation of our problem. So we can formulate our problem as a constraint optimization where we want to find the optimal scheduler C that minimizes the average queue length across time and networks or links. So here there are two constraints. The first is a scheduling decision. The scheduler C takes in the network state and generate a schedule. So the network state include at least three items. That is the conflict graph, the queue lengths of every links, and the link rates predicted for every links. Of course, we can also include more items such as the total waiting time on each node. The second constraint is the queuing state evolution. So here, this basically says that the queue length of the next time slot equals to the queue length of the current time slot plus the new arrivals minus the departures if this link is being scheduled. So this formulation is very difficult to solve because of the three challenges. First, the C involves solving an NP-hard problem. And secondly, both the arrivals and the departures, here's the link rates, are stochastic. And third is that we need to address the dependency between time slots.
To address the optimization problem, we developed this downstream pipeline, which include a graph convolutional network followed by a local greedy solver. So the graph convolution network takes in the link features and the conflict graph, and then output utilities. And then the local greedy solver takes in the utility as well as the conflict graph and then generate a schedule. So the local greedy solver ensures that all the schedule being generated meet the orthogonality constraint. The implementation of the GCN is here. From a system level, we have this equation here for a single layer in the GCN. So XL minus 1 is the input feature from the previous layer, and the theta 0 and theta 1 L are the trainable weights of this layer, and the calligraphic L is normalized Laplacian of the graph. And this we have this sigma as the vertex-wise acceleration function. And this GCN can be implemented in a fully distributed fashion. Here we have an example of one layer GCN with a scalar node feature, which is the product of queue length and link rate. So at a particular link or particular vertex, the output can be expressed in this equation. Now let's look at the second half of the pipeline, which is the local greedy solver. So this local greedy solver is an iterative process. In each iteration, every node will compare its utility with its neighbors. Right? Then the nodes that has the maximum utility in its neighborhood, for example, this one will be scheduled. Then the scheduled links will broadcast a control message to its neighbors so that they will be excluded. So now the undetermined links in this process, here's this one, it forms a residual graph, and the process will repeat on the residual graph until all the links are either scheduled or excluded. For the complexity of this downstream pipeline, because it's a distributed process, so we look at the local complexity, which is how many rounds of information exchange between nodes and its neighbors. For the GCN, this complexity is equal to the number of layers. And for the local greedy solver, on average, it has a log complexity to the size of the network. So this low complexity ensures the good scalability of our schedule. Notice that this local greedy solver is non-trainable, is not differentiable. So this makes the training of our approach very difficult.
To train the GCN, we use a customized reinforcement learning approach adopted from our previous work, which basically trains the output of the GCN through a target vector role. So here, to get the target vector role, we will set up a virtual environment of scheduling. And so this environment will draw a random conflict graph and generate realizations of random packet arrivals and link rates. At a given time t, from a given network state, we will run two different scheduling policies. One is the baseline policy, another is the GCN policy. And these two policies will be run k steps based on the same realizations of arrivals and link rates. And so they will make different decisions, and they will generate a series of cadences. And then our reward signal is designed by the ratio between the baseline cadences over the GCN generated cadences. And then here's a function 5. This could be either a linear function or a step function. So basically this reward says that if the baseline generates longer cadence than the GCN policy, then the GCN policy is a success and it should be rewarded. And our reward is imposed to the links that have been scheduled at time t, so basically at this step. And then this row, the vector row across the network, is the target vector for the utility. So we minimize a root mean square loss function to optimize the weights of the GCN. Next, let's look at the performance of our GCN-based scheduler on different topologies. So here we have a single layer GCN with the input feature as the product of cadence and link rate. So this is also the input feature, input utility for our baseline scheduler, which is a local greedy scheduler. We generate random arrivals and random link rates to emulate the fading effects. And we set the traffic load as light to moderate. We tested our schedulers on small to medium sized networks with tens to hundreds of links. And here on the x-axis shows the different graph models for the conflict graph. So the Argonaut-Shreni star Babausi-Albert Power tree model. So these different models has different underlying network topologies. And the numbers here shows the peak to average node degree. So the larger the number is, the more concentrated the conflict graph is. And the box plot shows the relative cadence of our scheduler, so which is normalized by the baseline. So here the 1 is the baseline. The smaller the number, the better the latency performance is. As we can see that for the median relative cadence, our approach can improve latency on highly concentrated conflict graphs. Meanwhile, for the worst case cadence or the worst case latency, our approach only causes slightly degradation. So this shows that our approach can improve the experience of most of the links in the network with the minimal impact on the worst case experience. Next, let's look at our performance on different traffic loads. The previous experiment shows only a moderate loaded traffic. As we can see that across different traffics, our scheduler also have a consistent improvement on different types of topologies. So this shows that our approach, our scheduler can generalize to different traffics as well as different topologies. To sum up, in this work we proposed a GCN enhanced distributed scheduler that keeps the good features of a traditional distributed scheduler, that is follows the hard constraint and is fully distributable. And we can explore the topology of the network to improve the latency. And our approach can generalize across different graph distributions, sizes, and traffic loads. For the future, we'll focus on how to integrate the delay-aware utility and the topology-aware utility, and also develop a principled learning approach for this non-differentiable pipeline. So here's the reference of this work. This is the end of this talk. Thank you for your attention. Please leave your comments or send us emails for any questions. Bye.